Okay, let's start with section 2.8, which is called one-to-one functions and their inverses. One-to-one functions and their inverses. One-to-one functions and their inverses. So an inverse function, for now, we're going to officially define it, but for now, let's say an inverse function, which is going to be the main idea for this section, an inverse function. And let's just talk about it kind of in a non-technical sense at first. An inverse function should, quote unquote, undo a function. For instance, let's take the function f of x equals 2x plus 3, and let's take another function g of x equal to x squared plus 1. Okay, let's look at f of x equals 2x plus 3. Consider what this function does to x. It takes x in as an input, multiplies it by 2, and adds 3. So a function that undoes f of x here could be undoes, is that even a grammatically correct word? Whatever. It undoes the operation, the operations that this function does to x. That undoes f of x could be, what do I call it? Later we'll have a name for it. Let's see, what's the opposite of 2 times x plus 3? I need to take x and subtract 3 and then divide by 2. I do the operations in opposite order. So if the first operation, so I go times 2 plus 3, and if I want to come back out, I do minus 3 divided by 2 in the opposite order. Going in, times 2 plus 3, coming out, minus 3 divided by 2. And I'll go ahead and tell you what the notation is, even though I haven't really introduced it yet, but an inverse function notation is going to be the same as the original function. So here's the original function, and then for inverse function, we put a little -1 in the superscript position between the f and the little parentheses x part. So this is read as f inverse of x, or you could read it as f of x inverse. That's fine, either one. But the point is that whatever this function does, this one does it undoes it. It does the opposite, right? So what does this mean? What does this mean? For instance, if I plugged in, wait, let me get my colors right here. Okay. F, so this function of, say, 7 is going to be 2 times 7 plus 3. So it takes in that input of 7, multiplies it by 2, and adds 3. That gives me 17. So I'm getting f of 7 equals 17. So I'm getting f of 7 equals 17. Then f inverse, now we're going to come to this g of x function, but for now I'm just talking about f here. F inverse, what does this mean? That means that if I plug in the output of this function f, which took in an input of 7 and it gave an output of 17, input of 7, output of 17. So now if I flip that and I give it an input of 17, I should get 7 here. Let's see if I do. 17 minus 3 over 2 is the same as 14 over 2, which is 7. So f inverse of 17 is equal to 7. Oh, I guess if I'm going to do that with my 7s, I should probably do that on all of them. So the point is that if f of 7 is equal to 17, then f inverse of that output 17 should be equal to 7. They undo each other. So as a picture, input of 7 into the function f of x. So the f of x is a box here, and we get an output of 17. So now if I flip that input of 17 into my inverse function, I get an output of 7. Cool. All right. Oh, one second. Okay, good. Now, let's talk about that g of x function. So I'm just introducing you to this idea of what inverse functions should do. All right, g of x is x squared plus 1. All right, so if I said find an inverse function, you might say, okay, well, I know I square x and then I add 1. So I'm going to do those in opposite order, -1, and then take a square root. Does that make sense? Hopefully that makes sense. That those are the opposite operations. So I'm going to take x, and I'm going to subtract 1 from it, and then I'm going to take the square root. Now, when we talk about building inverse functions, there will be a better process later. I know we're just doing it in words right now, which might seem a little difficult, but don't worry. Now, this is going to be a problem. I'll show you why. Because, how can I say, let's see. Oh, I just had a brain fart. Hang on, let me get caught up here. Oh, yeah. Okay, so if I plug in, say, I'm just going to pick some numbers, right, just like I did here for f and show that, you know, one input gives an output and then reverse that, and it should work in reverse, right? Okay, so let's say I plug in g, let's just pick 2 just to make it easier, right? So that's going to be 2 squared plus 1, which is equal to 5, all right, 4 plus 1. So I have, just to clean this up, g of 2 is equal to 5. So I should expect g inverse of 5 to be equal to 2. Is this true? Well, g inverse of 5 is equal to square root of 5 minus 1, which is square root of 4, which is 2. Okay, cool, no problem. All right, so what's my point? Because I told you that this is not going to be a good example of an invertible function because it's not. Well, let me show you. What about if I did this? If I said g of -2 is -2 squared plus 1, which is still 5, which is fine. A function can do that. It can take 2 different inputs and give a different output. That's legitimate. But now, when I invert that, g inverse of 5, but I've already calculated g inverse of 5 is 2, not -2. So something is wrong. Let's investigate. Okay, let's investigate. So g inverse only worked for one value, right? So the problem is, well, let me say it. Let's investigate that a bit further. Consider the function g of x equals x squared plus 1. It can yield, it does this special thing where it can yield the same outputs for 2 different inputs. What do I mean by that? Well, like g of 2 is equal to 5 and g of -2, so different input, 2 different inputs being a 2 and a -2, but it yields a 5 as well. How does that look on the graph? 2 different inputs, that means 2 different x values. By the way, what does this x squared plus 1 graph look like? It's a parabola that's been shifted up by 1, right? Just quickly graph that. 2, 5, so input of 2, out, whoops, wait, 1, 2, 3, 4, whoops, there's 5. 2, 5, and -2, 5. So here's my parabola. So what's happening is, if I was to draw this relationship right here, that I wrote down g of 2, so where's g of 2? G of 2 is right here. Input of 2, output of 5. Input of -2 over here on the x-axis, -2, same output of 5. It's hitting 2 outputs at the same sorry, I said that backwards. It's hitting the same output, hits the same output of 5, same Y value of 5 for 2 different inputs. Let's write that down. Hits the same Y value, or I'm going to say output, for 2 different inputs. Okay, so why is that a problem? Because when we try to invert this, if we want to invert this, so here's the big problem. When we invert this function, when we try, I should say, to inverse this function, we'll say invert or inverse, using inverse as a verb here. When we try to inverse this function, we end up with something that is not a function. Why? Why? Why do we end up with something that's not a function? A function is allowed to do this. This is okay. A function can hit the same output for 2 different inputs. But a function, when I try to invert it, my inputs and outputs are swapping, right? My inputs, that's what an inverse function does. We haven't really totally defined it, but back here, this little picture shows the input and outputs are swapping for an inverse function. So when the inputs and outputs swap, we end up with this situation. And I'm going to write it. It's this thing that I wrote in blue over here, except inputs and outputs are swapping. So I'm going to say hits the same input. No, wait, that doesn't make sense, does it, grammatically? I'll say it this way. The same input hits 2 different outputs. See how input is swapping with output here? Like literally in this sentence, except I have to adjust the grammar to make it make sense, right? The same input hits 2 different outputs. Is that a problem? That is a problem. That is not a function. This fails the definition of a function. Okay, so what's the point? Functions like g of x equals x squared plus 1 that hit same output for different inputs are still functions. They're like these functions. It's still a function, but it cannot be inverted. A lot of writing, a lot more writing in this, right? There's a lot to say about these ideas, or this idea of invertibility for a function. Functions that hit the same output for different inputs cannot be inverted. As a picture, what does this mean? As a picture, any kind of function that's going to do something where it overlaps on itself from left to right. That's a wild looking function there. So right here, it's hitting, boom, same output here and here at 2 different, oh, and again, at 3 different inputs in this case, because I drew a pretty wild function. So it's hitting this same output for 3 different inputs, which is okay as a function, but this cannot be inverted. This cannot be inverted. This function, as this red line, whatever kind of crazy function this is, does not have an inverse. Okay. We're going to talk more about the picture and everything. Still just kind of warming up a little bit here to the actual technical definitions. So what makes that f of x equals 2x plus 3 special? Because remember, that was invertible, no problem. It only hits one output for each input. Right, if I was to graph this, it's a straight line, right? 2x plus 3, y-intercept at 3, slope of 2. It's never going to fold back on itself, right? So it only hits one output for each input. We say that it is 1 to 1. So hence the name of the section here, 1 to 1. For a function to have an inverse, it must be 1 to 1. Okay. Here's a little diagram. Let's consider f of x equals 2x plus 3, and then use that counter example, g of x equals x squared plus 1 over here. And let's draw some little diagrams here of inputs going to outputs. Inputs and outputs. Okay, so let's just pick some generic numbers here, like 1. Plug in a 1 over here. What is f going to take that value to? I'll plug in a 1. We get 2 times 1 plus 3 is 5. How about a negative 1? Negative 1 times 2 is negative 2 plus 3. That gives me a 1. That's fine. How about 0? 0 is going to be 2 times 0. 0 plus 3 is 3. Okay, this is fine. This is an example of how this function is 1 to 1. Now let's look over here and see how that contrasts over here with this g function. Okay. By the way, this little red line I'm drawing, this is showing the function f carrying one value and input over to the outputs. Okay, so let's pick 1. 1 squared plus 1 is 2. How about negative 1? Negative 1 squared is 1 plus 1 is 2. Wait. That's a problem. That's a problem. Because really what's happening is this is going to the same value. In fact, honestly, I didn't mean to draw it like that. Let me fix that. Here's my inputs. Here's my outputs. 1, g is carrying 1 to 1 squared plus 1 is 2. That's g carrying it. And then g carries negative 1. Negative 1 squared is 1 plus 1. Carries it to the same output. And then just for fun, here's 0. 0 squared plus 1 is just 1. So that's a different output. But this is the problem, right? This is the problem. This function will never do that. This function, everyone has a home, a unique home. Every input has a unique output. Everything is paired off by this function. Whereas in this function, some of the inputs are sharing an output, right? This is 1 to 1. This is not. Okay, how does it look on a graph? Well, I've kind of already drawn that, but let's officially define it. A function is 1 to 1 and hence has an inverse, right? That's really, those go hand in hand. If and only if, it's just a fancy way of, I don't even want to get into it. It's just a fancy way of saying that it's always true. No horizontal line intersects the graph in more than one place. Or we'll just say more than once. This should call to mind the vertical line test that we had for functions, but this is the horizontal line test. We call this the, this is the horizontal line test. What do we say for functions? No, because we're not testing if this thing is a function. We're testing if it has an inverse. So we'll say horizontal line test for inverse functions. It's a longer name, a little bit more of a mouthful there. Okay. So as an example, f of x equals 2x plus 3 does pass the horizontal line test. I'll quickly graph that function. 2x plus 3, so I'm just going to quickly sketch there. I'm not going to worry about officially graphing it. And if I run horizontal lines, any horizontal line through this, it's only ever going to hit that red line in one spot, no matter how many I make, right? Contrast that with g of x over here equals x squared plus 1. Oh. And again, just a real quick sketch of that. This will fail. So this passes the horizontal line test, meaning it is 1-to-1 and it's invertible. Over here, this fails, right there and there. It's hitting twice, so it fails. So hence it is not 1-to-1 and not invertible. F of x here is 1-to-1 and invertible. This one is not 1-to-1 and hence not invertible. Here's a technical definition of 1-to-1. I've drawn you a picture, given examples, drawn the little input-output diagram, but let's get the official definition down. This is going to be less intuitive here. A function is 1-to-1 if we have hang on. If we have f of x sub 1, so some input, equals f of x sub 2, some other input, implies, here we go, implies that x1 is equal to x2. Let's look at how we can use this definition for those two functions that I worked with. Okay, so f of x, let's talk about f of x equals 2x plus 3. How the heck do I use the definition to show that this is 1-to-1? Well, I take two random x values, which I just say x1 and x2, and I say their functional output should be equal to each other. So f of x sub 1 equals f of x sub 2. That's going to mean, so literally plugging in x1 on this side, x1 into this function is 2 times x1 plus 3. On the right-hand side, I have 2 times x2 plus 3, literally plugging in x2 into the function here on the right side, left side, right side. But then what happens here if I try to like clean this up? Subtract a 3 from both sides and I end up with 2x1 equals 2x2. Divide by 2 on both sides, and what do I end up with? x1 equals x2, which is exactly what I needed. this implied that this relationship implied that, so the outputs being equal means that the inputs are equal. How does that translate to the picture? That means if you give me two outputs and you're saying that they're equal, so two outputs which really are equal, so like just one little output laying there, that should correspond to only one input. So I'm saying, like, pretend like there are two distinct, pretend like there are two distinct ones, but then in the end it really just turns out they're exactly the same. Those inputs are falling at exactly the same spot right there. Let's contrast that with this g of x function. Oops. All right, so I'm just going to lay this on top here. Let's look at g of x equals x squared plus 1. So now I'm going to try to apply this definition. See what happens. It should break down somewhere because I know this function is not one-to-one. So I'm going to say g of x1 equals g of x2. I'm going to go ahead and assume that, and I'm going to try to get here. And by the way, why is the letter name changing? Well, because the name of my function here is g, right? Okay, so g of x1 is x1 all squared plus 1, x sub 1, that's sub 1 right there. And that should be equal to x sub 2 all squared plus 1. Okay, now I'm just going to proceed through the algebra just like I did a second ago with the f of x function. So subtract 1 from both sides, so I'm getting x1 squared. Do I really need the parentheses? Probably not, but that's okay. Subtracting 1 from both sides. Now when I square root, what's going to happen here? When you're square rooting in an equation, you have to remember, when you're square rooting in an equation, like if I have a squared equals 49 and I square root both sides, sorry, 1 second. Trying to make sure Teams froze on me whenever I was recording for my 110 class and it's acting weird. Okay, I think it's good. Whenever I square root in an equation like this, I have to add the plus or minus, right? The plus or minus. Because both, in this case over here that I drew, 7 and -7 satisfy this equation. That's going to hold. That idea is going to hold here. So I have, well, what do I have? Plus or minus x1 is equal to plus or minus x2, meaning they might be the same sign or they might not be. So I don't end up with this pure relationship, just x1 equals x2. I end up with this weirdness where I can say, well, I could have like a positive 2 and a negative 2, which is exactly what happens in this picture. Right? I say that if you give me two of the same outputs, so I pick a y value like here, but what happens to this function? It says, well, I can either give you like a, this might be like a 2 or a -2, for that same output. But that's not good enough for the definition of one-to-one, right? One-to-one insists that there only be one input for every output. So this fails. Cool. All right. So now that we've gotten out of the way the conditions that you need for a function to be invertible, let's talk about actual invertible functions and like how to build them and what they do a little bit more. Oh, actually, let me make some notes. Let me make some notes here. Let me give you some facts that will be helpful. For our purposes, the even functions we have are not invertible. So things like, the parabola x squared, right? You see why it's not invertible. It's going to fail that horizontal line test. Or maybe, so this is like f of x equals x squared. Or maybe like a 1 over x squared. That would also fail, right there and there. So when you see a function like a power function or a reciprocal function that has an even exponent, they're not going to be invertible. Now the odd ones will be like x cubed and 1 over x cubed or 1 over x. Linear functions, those are going to be invertible. Okay, so that's just a little fact there that we should note. Okay. Okay, here comes an example. Sorry, have I enumerated any examples yet? Nope, just been talking a whole lot. Okay, so let's actually run an example here. Example 1, just to make sure we're all good with so we've talked about the conditions for invertibility. Let's actually start working with some inverse functions. Baby steps though. So if f of 1 is equal to 5, f of 3 is equal to 7, and f of 8 is equal to -10, find f inverse of 5, f inverse of 7, and f inverse of -10. So I'm introducing that inverse function notation again here. Some water. All right, here we go. Not a whole lot to say here. F inverse of 5, you're going to find where the output is 5. There it is, output of 5. That input is 1. Inverse function swaps input and output, so I'm getting a 1 there. Okay. F inverse at 7, so look at the original functions, which one outputs a 7? There it is. With an input of 3, my inverse function swaps that input and output, so I get a 3. I think you're getting the picture now, right? F inverse of -10, looking for an output of -10. What input gives that? An 8. Inverse function swaps those. So input of -10 now gives an 8. Okay. Let's talk about building an inverse function algebraically. Domain A, that's input. This is what I like to call input. Range is output. I'm just using capital letters to denote the name of the domain and range. These are probably intervals, like we've seen intervals on the number line. That's what A and B are representing here. Function with, okay. Then its inverse function, denoted by F inverse, has domain, well, it swaps input and output, so it has domain B and range A. So you see how that domain and range are flipping, input and output are flipping. We define it by if you have f of x equals y, so some input x for some output y, and that can be inverted to give this relationship. F inverse of that output yields that. It flips them, right? Flips them. And technically this is for, we're not going to get into these domain and range issues, but it's technically for only for any y in B. So the input of your inverse function has to be from that, has to be in that range. We get into a little bit of weirdness there. I don't want to talk too much about this. I found when I taught teaching trigonometry this semester, you do have to get into some of these issues in great detail to define some inverse trigonometric functions. So if you go on to take trigonometry, you will see that there. And as an instructor teaching trigonometry this semester, I found plenty of time to go into great detail about that. And I even used some examples from 112. So for now, I'm going to kind of brush this issue aside for any y and b, just kind of pretend you don't. Here's what I need you to know. Inverse functions swap inputs and outputs, okay? And this is the notation. If you got an inverse, or you got a function, here's what its inverse looks like. Now, you may have noted that whenever I was writing the inverse functions, I was putting an x back in there for domain variable or for input variable. That's going to be kind of standard notation. This is just kind of like writing. This is trying to emphasize the point that inputs and outputs are swapping. But when you actually write your inverse function, at least the way our book does it, we'll put an x back in as the little placeholder variable. You'll see what I mean, because we're about to build some. Where do we go to do that? Okay. What is this example 2? Find the inverse of each function. So I'm going to say A is f of x equals 3x minus 5, and g of x, we'll do two linear ones. Oops, part B, g of x is equal to, I don't know, 4 minus 6x. So that's fine. All right. How do we find the inverse function? So I've already kind of done this in words. I've said you need to identify what's happening to x, identify what's happening to x, and undo it, right? So I see a times 3 minus 5, but let's walk through like a bit in more detail about, can we write down more details about that process? So part A, starting off with f of x equals 3x minus 5. What I'm going to do is I'm going to say, all right, f of x here is representing my output, right? And x is representing my input. Let me replace this f of x notation with just the letter y, because on the graph, on a coordinate plane, we tend to think of the horizontal axis as x and the vertical axis as y. Now, if I put that in terms of inputs and outputs, when you graph a function, you've got input values on the horizontal axis, the x-axis, and output values on the vertical axis, the y-axis. So let's replace this f of x temporarily with just the letter y to represent those output values. In our next step, what does an inverse function do? It swaps inputs and outputs. It literally swaps x and y values, or inputs and outputs, right? Horizontal axis with vertical axis. It literally swaps them. Let's reflect that here. Look, literally swap inputs and outputs. Now explicitly, what did I do? I swapped x and y, right? Swapped x and y. Okay. In my next step, now this y is now different than this y, right? This y represents the outputs for my original function. But now they've swapped, and now I'm letting this y now represent the outputs for my inverse function. So what I want to do now is solve for y. So now I'm going to solve for y. So in this next step, these next few steps, I'm going to solve for y. This is where the algebra comes in. So add 5 to both sides, so I'll have x plus 5 is equal to 3y. Divide by 3 on both sides, so x plus 5 over 3 is equal to y. Flip it around because we like to have that isolated variable on the left-hand side. And now rename these. What does the output look like for an inverse function? We like to use this nice notation. F inverse of x is equal to x plus 5 over 3. There it is. So that last step. Replacing y with f inverse of x. So you see most of the work is happening here in the algebra, but really the critical step is when we are doing what the inverse function actually does, which is right here, swapping input and output. So this y is now becoming the output for our inverse function, hence why we want to isolate it. All right. These steps, you'll want to have these written down. These steps are going to work for finding any inverse function. Oh, part B. Almost forgot about part B. Okay, let's do part B. Okay, I'll run through this one quicker. So, looking at those steps, in fact, you should try and find this one. Pause the video and try to find this inverse function. All right. Replace g of x with y. Swap x and y. Solve for y. Oops. Okay, subtracting 4 from both sides. 6 is still negative. Divide by negative 6. Oh, gosh, sorry, this paper keeps scooting around on me. Divide by negative 6 on both sides. So I'm going to, can I fit it here? Yes, x minus 4 all over negative 6 is equal to y, so that's y there. So y is equal to x minus 4 all over negative 6. Which, by the way, I could deal with that. I could pull that negative up here, which would flip the signs up here. So it'd be 4 minus x all over 6. So what's happening there? I'm saying put the negative up here, which gives me negative of x minus 4 over 6 if I stuff the negative up here instead of in the denominator. And that's the same as negative x plus 4 over 6, and that's the same, just flipping it around, put the 4 first. Okay, so a lot of little shenanigans going on there, but essentially I'm just saying put the negative up there and it changes both of these signs, and then I like to flip it to have the number up front being positive. Now let's look at the original function. Oh, wait, sorry. Now the last step is to write this as an inverse function. G inverse of x is equal to 4 minus x all over 6. G inverse of x is equal to 4 minus x over 6. Let me contrast that with the original function g of x. So g inverse of x is equal to 4 minus x all over 6. What does this function do? It takes x in, it multiplies it by negative 6, and then it adds a 4. You can think about it like that, or you could think about it as taking in a 6, taking in an x, multiplying by 6, and then taking that and subtracting it from 4. Kind of more of a mouthful to say this one because the x is happening back here. So in the opposite order, I'm taking the x, negating it, then adding 4, and then dividing by 6. So you can see how, as the functions get more complicated, it's kind of harder to write down their inverses just by describing them in words. So if you remember from the beginning, I gave you a function that was kind of easy to write down in words, like to find its inverse in words. Here it is. Takes in x, multiplies by 2, and adds 3. So its inverse does that in reverse order. Subtracts 3 and then divides the whole thing by 2. maybe that makes, that makes good sense there. But as soon as the functions get a little bit more complicated, because this isn't even that much more complicated, it's still linear, but it's got a minus sign and the x is over here, so it's slightly more complicated. Making sense, like doing that in words to go from here to here just in words would be pretty difficult, right? You probably want to manipulate it a bit before you tried that. This process, though, that lets you get from this to this by the process I just did is pretty relatively, well, it's easier, right? The process is going to be better here than trying to do it in just in words. Let me add another, let me say part C here. Let me say h of x is equal to x to the fifth minus 3 over 2. Now, is this invertible? Yes, it's fine. It has that odd exponent, so we're good. It's invertible. I'm never going to give you a function that's not invertible and ask you to find its inverse. All right, so solving part C, clearly, I mean, it's right there, but I'll rewrite it anyways, just for sake of completion. Okay, so first thing I do is I replace the function notation with the letter y. Then I swap x and y. So I say x is equal to y to the fifth minus 3 over, only the letter swap. Everything else stays exactly put. The little exponent of 5, the minus sign, the 3, the fraction, the 2, all of it stays put except the x and the y. It's like you literally erased the y and wrote x and erased the x and wrote y. Everything else is exactly the same. Now I need to solve for y. How do I solve this for y? Now I'm going to work a bit horizontally just to save vertical space here. Try to use more of my paper. So first thing I'm going to do is multiply by 2 on both sides. So I'm going to be a little bit more explicit in what I'm doing here. I'll actually write it out so you can see what I'm doing. I'm going to multiply by 2 on both sides. That's going to effectively cancel this 2 and the whole fraction part on the left, on the right side. Left side is going to be 2x now, and then I'm going to have y to the fifth minus 3. Now the next step, I'm going to add 3 to both sides. So I've got 2x plus 3 equals y to the fifth, effectively canceled out that minus 3 by adding 3 to both sides. And of course, these are not like terms, so this is all I can do here. Now what do I do? Let me write my little arrows here. Okay. Try to get the whole function there. Okay. Now what I need to do is take the fifth root on both sides. So how do you undo y to the fifth? You take the fifth root on both sides. That's going to clean this up and pop out just a y. That's what I want. Now the left-hand side looks like a mess. Here it is, but that's it. That's the inverse function. But I'm still not quite done, right? Because I need to say, I need to flip it around and say y is equal to the fifth root of 2x plus 3, and then go ahead and write it in inverse function notation, recalling that my original function was called h of x. So my inverse is going to be h raised to the little minus 1 for inverse there, fifth root of 2x plus 3. In the original function, just so because I can't fit it all here, just so you remember, was x to the fifth minus 3. So here's my inverse function and my original function. So the original function takes in x, raises it to the fifth power, then subtracts 3 and divides by 2. Does a whole lot, right? Fifth power minus 3 divided by 2. Over here, it does that in the opposite direction. So remember what I said. What was the operations here? Fifth power, then minus 3 divided by 2. So going in reverse order, times 2, right? Because working inside, times 2, add 3, then fifth root. So it does those operations in reverse order. That's what this does. Let me say one more thing about this step here, where I'm taking the fifth root on both sides. In general, if you've got some letter a raised to the nth power is equal to whatever stuff over here, it doesn't matter what it is, and you want to solve for a, then you take the nth root on both sides. I call that the nth root. So in this case, it's a fifth root. If it was a 3, it would be a third root. If it was a 7, it'd be a seventh root. Now notice I'm leaving out the even ones here because you would never try to find it for an even function because even functions are invertible. So that's what was happening. This is like in general. When I say stuff there, that's just whatever's happening on the other side of the equation. And notice I don't use plus or minus, right? Whenever you're taking square roots, you have to introduce that plus or minus thing. Remember, I talked about that earlier. But when it's an odd root, any kind of odd root, you don't need to put like plus or minus on your radical. In fact, that would completely mess up the invertibility of this function. Okay. Sorry, example 3, I forgot to enumerate it. Example 3, verify that h of x and h inverse of x are actually inverse functions. How do we do that? Two functions are inverses of one another. What are they supposed to do? They're supposed to undo each other. Yeah, okay, sorry, I just had to confirm something. If and only if, two things. F of F inverse of X. Okay, so what am I doing here? Remember from 2.7, this is composition of two functions, plugging one function into it. So I'm plugging the inverse into the other function. What should happen? It should just spit out whatever the input was there. And the opposite. Plug in the original function into the inverse, and it should just spit out that X value, whatever got plugged in originally. So think of it this way, like some function, it does, so let's think about this one. Some function does something to a number, then the inverse function undoes it, and it just spits back out that original input. And the same thing is happening here in reverse. So if we wanted to show that for h of x, for the h of x and h inverse of x that we just worked with, we would say, oh boy, what would that look like? H of h inverse of x, what is that? Well, here they are. H of x was x to the 5th minus 3 over 2. I'll write that up here. H inverse of x was the 5th root of 2x plus 3. Okay, there they are for reference. Am I going to regret doing this with these functions? Maybe. Let's see. I don't think it's going to be too bad. All right. So how do I do this? I literally write the h function, but I write h inverse in place of x. So I'm going to have my -3 and divided by 2, but instead of x to the 5th, I'm going to have h inverse of x to the 5th. That's my new input. Instead of x, it's a whole h inverse of x thing being plugged in there. So see how that x is literally being replaced by h inverse of x. But I know what h inverse of x is. It's this big thing. Okay, so here we go. Here we go. I'm gonna draw my big fraction bar, 2, -3 at the back. Okay. Got this whole big thing raised to the 5th. Now I'm ready to, I've got it all set up. This is what's going inside the parentheses. This h inverse of x gets stuffed right here. So the 5th root, 2x plus 3. Okay, good, good, good. But now what happens here? I've got a 5th root raised to the 5th power. They cancel. So I've got, that's nice because that's like the worst thing going on here, and all I'm left with is 2x plus 3, that -3 at the back, and then over 2. What happens here? +3 -3 cancels. 2x over 2, those cancel. Everything cancels, and I'm just got left with x. That's the first condition satisfied. Remember, there are two pieces to this. The first piece is to plug the inverse function into the original and confirm that you get x. The second piece is to do it in reverse and confirm that you get x. So now I'm going to check that h inverse of h of x is equal to x. Let's see if it is. H inverse, I know that that function is that 5th root thing, so I'm going to write the 5th root, and it's 2x plus 3, but instead of x, I'm plugging in the entire h of x function. So instead of 2x plus 3, it's 2h of x plus 3. This one's going to look a bit worse, but just stick with me here. So it's all under a 5th root. I have twice h of x. So let me put, how much room do I need for h of x? Like that, and then plus 3. So now I'm plugging in h of x, which hopefully you have written down on your paper, right? So I don't have to rewrite it down for reference. H of x is x to the 5th minus 3 over 2. Literally just substituting h of x here, right? Now let's start cleaning it up. Ready to do some algebra here. This 2 is applied to this whole parentheses thing, but this whole thing is divided by 2, so those 2's cancel. Okay, that's nice. I have x to the 5th minus 3 plus 3. Notice those 3's cancel. They cancel each other, and I'm just left with the 5th root of x to the 5th, but the 5th root and the x to the 5th cancel. Look at that, just x, just x. Nice. The setup is tough, but then the algebra, it's like setting up dominoes, like hard to set up, but then it all just tumbles down and you end up with just an x here. That's how you confirm that two functions are in fact inverses of each other. So what did we end up getting? What did we end up getting? We have, since h of h inverse of x equaled x, and, because we checked both directions, h inverse of h of x equals x, they are definitely, like, we were already sure of it because we built it, right? We literally built the h inverse function as part of a different example, but this was just confirmation. So now we are sure they are definitely inverse functions of one another. And when I say of one another, I do mean that they are both inverses of each other. Now, only one of them is getting that special inverse function notation, but they are in fact inverses of one another. Okay. We're not going to graph the inverse. Okay, give me, oh, look at that. That's like almost perfectly at an hour. But let me look at the homework from the text. Oh, you know what I'm going to do? This is good. I'm going to show you guys where these problems are that I give to you to mark for review because my trig class could not find them, and I'm worried now that because you guys also use WebAssign, they weren't able to find the ebook. I'm not really sure why, but I want to make sure you guys know where it is too. So I'm logging in. Just give me one moment, and then I'll share my screen. I'm going to go to student view as well, so we're seeing exactly the same thing. Okay, screen share. Okay, so this is what you should see. You're going to go to, of course, our class. Maybe you don't even have to do this because you only have one WebAssign class. Okay, and then you're going to go to My eBooks. So this is where the book is. And then, yes, click. And then, so those problems I marked that I say mark for review are from the textbook, from the back of each section. So for example, in this section, I give you a lot in this section because this is a good section to look at. So we're in chapter 2, functions, section 8. Let's see, where is it going to put me? Yeah, good. So go to all the way down to chapter 8, and then I'll go to exercises, can go straight there. And the ones I gave you to do, well, they're in the chat in Teams, but it's 7, 8, 9, 10, 27, 37, and 39. So this is where you're going to find them. So first question, 7, 8, 9, 10, or the first four are right here, 7, 8, 9, 10. And it says, determine whether each function is one-to-one. So you're going to be looking at using the horizontal line test. Look, this one would fail right around here, right? It would fail. So if I look at the answer, it's going to say no, right? It's not. Now, they don't all have answers, just some of them have answers. This one is fine. It gets a little close here, but it is fine. That is invertible because it passes the horizontal line test. It gets a little close here. If it bubbled up a little bit more here, it would be in trouble because it'd be more like this one, but this one is okay. 9 is definitely okay. So let's see, it should say yes, yes. Definitely invertible because it passes the horizontal line test, so it is one-to-one. And this one definitely fails. 10, it's good, it's good, it's good, but then right here, it hits tons of values right here, right? So that's bad. It is not one-to-one. It is not invertible. It fails the horizontal line test. Okay, then what was it? Which 27, 37, and 39. What are the instructions here? Find the values of an inverse function. Assume that f is one-to-one, so assume it has an inverse. Here we go, 27. If f is equal to 5 minus 2x, find f inverse of 3. So the way you would do that is find the inverse function, like we did in one of our examples, find the inverse function, and then plug 3 into it. So what would the inverse of this look like? Well, you'd have to figure it out, right? And then you would plug in 3. So you should get 1. Well, I thought they would give us more there, but and of course I can always work these out if you find it necessary. Okay. 37 says use the inverse function property to, okay, this is like the last example we did, showing that they're inverses of each other. Look at 37 and 39. Those are the ones I asked you to do. Aren't those are so much easier than the crazy one we did, right? So you would just show, you would and look, they didn't give them inverse function names. They didn't say like f and f inverse or g and g inverse or anything like that, because they're kind of pretending like they may or may not be inverses of each other. So you would plug this function in to f and see if you get x, and it should be like literally like 1 or 2 steps because these functions are very simple. And then you do the opposite direction. What's that mean? I don't know what that means. And then 39, you'll do the same thing. Plug this function in for x here, see if it all simplifies to give an x, and then vice versa. And it doesn't give solutions for that one. Oh well, that's okay. I believe they are. Yeah, it says show that they're inverses of each other. Yeah, they are. Both 37 and 39 should clean up very nicely. Okay, so that's where those questions are. So this is where you'll find all the problems to mark for review. So if you wanted to go look at 2.6, you would go scroll down to 2.6, go look at the exercises, and I gave 19, 20, 22, 29, 33, and 36. So you could go find those here. All right. Oh, okay. That is it for section 2.8.